afternoon to all. Welcome to the rescheduled session. The session will start soon at 12:15. Thank you for your cooperation. Hello, Jeevas sir, are you audible? Hello, Jeevas sir.
Yes.
Okay. So shall we start the session?
Give me 5 minutes.
Okay.
2 minutes.
Okay.
Sure, let's start. Yeah.
Okay. So good afternoon once again, all the audience. Thank you for your cooperation. Let's hear Mr. Jeevas again. Over to you, sir.
Thank you. Shall I present now?
Yes.
Welcome all. Sorry for the inconvenience. Let's try to do this right this time. So welcome to this brief talk on things of future, past and present. So this is not a deep dive session on one particular topic. This is a shallow skimming of all the topics that you can choose to further deep dive after this session at your convenience. About me, my name is Jeevas. I currently work at Singtel Optus at Sydney. I've been working in the IT and cloud and all these things for the past 18 years. I started at IAC Bangalore as a project assistant. So yeah, I did my college bachelor's in computer science from College of Applied Sciences, Vadakkad, and then master's in Bharatiya University campus, and then I started my career as a project assistant at Indian Institute of Science, Bangalore. Then I moved to HCL. Then I worked on several projects in Bangkok, Xerox, Sydney Trains, etc. So that's about me. Without further ado, let's move to the agenda. So today I will try to explain and define what is a smart thing, what is an IoT, what is the difference, and also I will try to explain in this brief period of time with whatever depth I can about the concepts that about the various concepts that you really need to understand before getting into the actual IoT development and IoT and embedded development if you choose to. Excuse me. So few of the concepts include SoC, system on chip, and microcontrollers. What are the tools? What are the software stacks? And then how to get started. And then if there is time, we'll have a brief Q&A. So let's define a smart thing or a smart device. A smart device is something which is a finite state machine which captures
Excuse me, sir.
a
Can you
reasonable.
start your
Yep,
presentation again? It's not here in screen.
it's not.
It's
Oh,
not
okay.
some black screen only.
Uh, can you see anything
Yes,
now?
yes, yes.
Because
Now
it
it's
still
clear.
stays
Now it's
sharing.
clear. It's clear, sir.
Oh, okay.
Okay. Okay.
So, do you want to go like this or you want to have a full screen? Because
As you wish,
I
sir.
don't know which one is.
Because if something is here in the slide, it is very low. I mean, size is very less for the text. Is there any
Okay,
problem
sure.
for making it a presentation? I mean, slideshow?
No. I was wondering if it's because of that it's getting disconnected. Anyway,
Okay,
let's
okay,
try.
okay, okay, sir. You can continue.
Yeah, yeah, sure. Um, so a smart thing is something which is a finite state machine. So it has different states it has to transit to when there is a list of inputs to be acted on. So a smart, the difference between a smart and a dumb thing is
Sir, sorry to
only
interrupt
in
you
the.
again.
Yeah.
This presentation gone.
Okay, so full screen is a problem then.
Yeah, yeah, yeah. Okay.
Okay.
Yes, yes. You can
Okay.
continue
So,
like this. Okay.
okay. Yeah.
Okay, sir.
Yeah. Okay. So the one example that I can slowly take you to what the difference between smart and a dumb thing is. A normal water kettle that has only two inputs, right? So it has input to press the button and it has the thermostat input to stop heating. So if you add a little bit more number of states, like if there is actually water present before starting, the minimum amount of water, if it is present or not, then otherwise even if a user press the button, it won't start. And second thing, if the in case of any error scenarios, like if the thermostat is not reporting the right temperature, to avoid catastrophe and fire, if the thermostat can take input from a clock, a real-time clock, where it can keep track of the time it has accumulated since the user pressed the button to turn on, then it will add a little bit more smartness. So like that, you can add the most common scenarios, all the most common scenarios, and turn a dumb device into a smart device. So that's what a normal smart device is. So what has happened is uh, this concept was there since ages, right? So the since the electronics and electrical, even in mechanical things, the things used to the people used to make things smart. So what has happened is excuse me for a moment. Where is the transit button? what has happened is the 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 integrated chip technology and the microprocessor technology and the electronics in general advanced so much so that the it is possible to develop systems which can connect to the same internet and the same network that usual computers connect securely, that is through TCP/IP, through application protocol like HTTPS and all, with using very low power, very cheap uh, electronic devices or electronic or integrated circuits. That opened up a whole new world where I previously I said that a smart device is a finite state machine, right? So the finite state machine needs inputs, and also it has the capability to produce some output. So when such kind of smart devices has the capability to connect to the internet or your local area network, what has happened is it 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 opened up the capability to accept inputs from the network and also to accept also to produce output that not only is restricted to that particular device but to something else out there in the network or the internet. So that opened up the Internet of Things revolution. It has only just started, but it's going to take off like in 20 years, where the internet or the smartphone in 10 years has taken. In another 10 or 20 years, it will be ubiquitous. Ubiquitous means it will be present, omnipresent. It will be in any device. There will be some amount of whatever technology that we are going to discuss in this presentation will be there. That's my prediction, but I hope it's true too. Um, so an example of internet thing is an internet connected light bulb, right? So it can be turned on or off, right? So it can be turned on or off using a remote. It can be turned on or off based on your based on the light in your room. All these things you can do, right? So that smartness is already there. So what has when we can add an internet connected capability to a light bulb or a light switch, what has happened is suddenly the light bulb can turn on or off based on the information from the internet, like when is the sunrise time, when is the sunset time, or from the user's calendar, like is he in home, right? All this became the input. So the state machine became so big, and it can also output to anything on the internet, like it can, depending on the, in case somebody press the button, right? So the user press the button, it can change the state, not only in a local state machine, right? Not only it can say that I am on in the local memory of the bulb or switch, it can also output that information to some server or some application that's there, which has a lot more capability, like sending a message to, or sending a notification to the user's mobile, or sending the state of a shadow of an application which the user can use to turn on the light. So even if you forget to switch off the light to go while going out, you can do it anytime using his mobile, which will again update that state in the application server. And that application server, whenever it gets a chance to connect to the light, if it is immediately connected, it will switch off. Even if there is an internet glitch, the application state will be maintained in the central server, and then it can switch off the light. So it became fault resistant and fault tolerant. So that way, um, the possibility became much higher to what to in the definition of smartness of any device. So that is essentially what is an Internet of Things is, at least right now. So going forward, it will evolve a lot because the artificial intelligence will come into picture. The edge artificial intelligence will come into picture. So the whatever the my so I'll come to that in a short time. So let's move to the next slide. This is screwing. Okay, so before going to all that, let's try to define. Is it clearly visible, or do you still want me to do something? Hello? Hello?
Hello?
Yeah, is it clearly visible, or do you want me to do
Yes,
something?
sir. It is visible?
Okay, okay. And can you read at least little bit or no?
Uh, can you please zoom the slides? Yeah, okay, sir.
Okay, okay. So the heading is gone. Okay. Okay. So before going into a little bit more advanced, let's try to define few concepts that you really need to understand um, to have in a level playing field, right? So without understanding few concepts, it's very difficult to understand the whole subject itself. So let's try to define, and I think most of you already know at least part of it, but still, let me go through it once again. So let's define what is an SoC and what is a microcontroller, right? So an SoC is a blanket term, right? So it just means system on a chip. So it's in context to a chip which is related to a processor, right? So it all started when people started making microprocessor. So what has happened is earlier there was microprocessor and later there was microprocessor. In the middle, what has happened is Intel in the 1980s created a very low power microprocessor by that day standard, because it started with the 404, then 8080, 80, 85, 80, 86, and all those stuff. So in the middle, so they have got some idea or some capacity where they can use the little bit older technology to create a low power microprocessor with some little bit of RAM and little bit of storage, and they called it the microcontroller, and targeted or marketed it to solve one particular problem only. So that happened. So that's called the 8051, and for a long period of time, it was like a microcontroller. When somebody refers, what they mean is the 8051 microcontroller, and when they say 8051, it's the microcontroller. So for a long period of time, it was that. So 8051 defined the microcontroller, or what is possible with integrating some subsystems, right? So then there are so many capable microcontrollers came. Atmel created the AVR. Atmel created much better 8051 like 89C3189, so many. And then other companies also, Microchip created PIC and all. So that is the microcontroller, and all those are very low power compared to a normal microprocessor for quite some time, right? So then what has happened is smartphone came into picture. Smartphone and even codeless phone, I think. So that required a lot more processing power than what that day's microcontroller was capable of. And then people started using the existing or one generation prior PC processor. So advanced RISC machines or ARM processor that is currently running all the smartphone and all was not really developed um, for smartphone use or anything, right? So it was based on Britain's own company trying to develop Britain's own computer. So they created their own processor. That was ARM, right? So then, but the ARM has got some feature because it is RISC based. It's not complex. It used less power compared to the normal PC processor. So mobile phone industry started using that, and then that area of expertise evolved slightly. So it always follows where the money is, right? So if there is money in smartphone, then people start investing, and then the technology evolves. So it's like a chain, right? So that way. That way, ARM come into picture. Okay, that's not the point. The point is when handheld devices became a lot more popular, people needed more in their devices, and then if you then the microchip industry or the integrated circuit industry started to compress and integrate a lot more stuff into one single chip. That's what the SoC is. So in a smartphone chip, they're used to the components integrated is more than what a 19 or even 2000s laptop or PC is, right? So they integrate a graphics chip into one, along with microprocessor, along with the image processing, along with the video encoding, decoding, along with all the normal sensor related small communication endpoints, and all this integration created SoC. So in this presentation, when I say SoC, it is this highly capable integrated circuit which has all these subsystems integrated, right? So when this is one track, and then there is a microcontroller track which is also trying to achieve the same thing, but in a low power fashion, right? So microcontroller industry started integrating before the normal processing industry or the application processing industry like smartphone or laptop started. So they have that leeway. So already a microcontroller which started with 8051 by just integrating CPU or the ALU, FPU, memory management, along with some memory, some RAM and some storage, started integrating a lot more in the middle, right? So they also started integrating all the communication bus, all the EEPROM needed, or whatever is needed for that particular industry. They also started integrating, and the microcontroller is also evolving. And then suddenly, what happened is, I think it started with the USB. So when earlier we used to have only serial port, parallel port, and then some special purpose ports for connecting special purpose devices. There was no the standard port for one thing. So then when the industry adopted USB, there was so much requirement for USB based devices. So a USB based mouse needs a USB based logic, right? So if you do a USB transceiver and then a microcontroller to generate the XY coordinate and then send through USB, to reduce the cost, they started integrating. So USB controller became a thing, right? There are so many microcontrollers which can talk USB. So because the peripherals industry needed it, right? So there is one single chip with a USB capability. You can write code to behave it as a mouse. You can write code to, so one microchip can be sold to all these keyboard manufacturer, to mouse manufacturer, to video camera, to webcam manufacturer, to USB mic manufacturer, to, so that started the revolution. Then came Wi-Fi. So what has happened is, so Wi-Fi when it started, when the Wi-Fi started, no PCs has got the Wi-Fi capability, right? So there was a PCI card, or and if you are lucky, you have a computer with USB, then you will get a USB Wi-Fi. And what has happened is the Wi-Fi standards keep evolving. But if you make Wi-Fi USB or Wi-Fi PCI fixed function device, like, then you your device became obsolete so soon. So what they did was they integrated just the Wi-Fi radio and then put a microcontroller core in it, and then the software can be updated at any time. So even if Wi-Fi standard changes little, or even if the Wi-Fi range can be improved by a little bit software taking, they can do it by just by a driver update. So that turned into the Wi-Fi microcontroller industry. And then what has happened is people started using Wi-Fi for even for their devices or this thing. So some companies opened up the Wi-Fi development kit. Then what happened is people understood that this is a general purpose microcontroller which is more powerful than the normal microcontrollers available at that time, and they can use it for many more purposes than as a normal USB Wi-Fi or a normal PCI Wi-Fi. So that became turned as a special purpose microcontroller, and they in some industries they will also mention as a Wi-Fi SoC. So in now we won't say that, but so and similar kind of microcontroller, if paired with not with Wi-Fi but with some other radio like Bluetooth or Zigbee, they are called the Bluetooth SoC, Zigbee SoC, and what they are I'll come later. So, and in this slide you can see the level of integration difference between a normal SoC in the on the right hand top side, like a OMAP, which was the earlier mobile processor, the level of integration in a original 8051, and the level of integration in one of the most popular Wi-Fi controller called ESP32, Express 32, which is one of the backbones, or which is one of the main chip driving all the internet connected devices like Wi-Fi switches, Wi-Fi bulbs. Around 90% of the IoT market relies on this ESP Expressive chip. So you can see the integration there. So I will come to that again later, but anyway. So now let's define the architectures in play. So what is an architecture? Architecture is nothing but a language. So you all know about a programming language, right? So programming language converts your whatever language, C, Java is a virtual machine, so C or what or C++ or Rust or Go into some machine language, right? So that machine language is defined by the architecture. So it's so architecture is a lot more than that, but from a program, from a developer perspective, you can say that it's the assembly instructions that defines the processor that you're going to compile it for, right? So let's take a look at the popular architectures and where they are used briefly and quickly. So we know x86, x86-64. It is a classic processor that is there in your PC and laptop. x86 is the 32-bit, and x86-64, which is developed by AMD, is the 64-bit version. We say x86-64 because there was in between Intel tried to develop a x64 and which failed in Itanium chip, and then AMD released x86-64, which became compatible to the original x86, and that became the standard for 64-bit in PCs. So this particular architecture is also used in some embedded devices like some high performance networking and storage equipment and some industrial application, but it's not really a real embedded architecture. Then there is the ARM Cortex-A. Cortex-A is one of the most popular architecture, which is most deployed also because of the smartphones, because of the tablets, because of many other smart speakers and all the smart TVs. All these things relies 99% of those kind of intelligent devices relies on that. There are many versions. There is a 32-bit version, and then there is a 64-bit version. The V7, V6 is 32-bit, V8 is a 64-bit, which can be adopted as a 32-bit. So that's what it is. Then there is MIPS. MIPS is a very good architecture for some very special use cases. So till 2008 2018 or even 2000, even now, it's one of the most used architecture in networking devices. Let's take your ADSL router or your Wi-Fi router, Wi-Fi modem earlier. All this has some SoC which has the MIPS architecture in it. So that's one of the most popular architecture, and it is one of the most popular embedded architecture also. If you are using embedded Linux, I'll come to that later. Then there is the RISC-V architecture. So that has the capability to change the world in a way that we haven't seen any time before. It's the first and foremost, it's an open source architecture. Anybody can copy so anybody can copy a RISC-V architecture and make an SoC. It was not that easy till now, but it's getting better. I'll come to that also later. So Indian government has adopted it as the official architecture for India. And then it is suitable for both microcontroller and SoC implementation. And we have free open source silicon organization, like free open source software. We have free open source silicon that's called FOSSI. So that has adopted RISC-V. Then there is ARM Cortex-M, ARM Cortex for microcontrollers. So that is not, we don't run Linux or Windows on Cortex-M, but we use some kind of operating system. We can use bare metal also, but some kind of operating system like Sapphire or FreeRTOS on it, and we can run multiple tasks in it, right? So a microcontroller usually runs only one task or one program. A more advanced microcontroller can run a full-fledged operating system with a scheduler with multiple tasks. You cannot run you can install whatever application on the fly, not like that, but you can have multiple things going on at the same time, at least, and then respond to within a hard real-time, soft real-time, depending on the priority of a task you can define. So that kind of capability Cortex-M gives. And then suddenly one architecture came into picture, and that architecture is not developed by any Korea, China, or anything. It was an architecture that was already there because it was there used in DSPs, digital signal processing, which is a very niche market. But in 2014, I think what has happened is there is a company called Espressif, which is a Chinese-based company. What they did was they took that extensor core, I think LX106 core, and integrated with a Wi-Fi radio, and created a very low-cost Wi-Fi chip, and also created a Wi-Fi small board, which has got a serial port and few pins for supplying power and one general purpose IO. So, and they marketed it to the hobbyist community to be integrated to their hobby projects, right? So whatever project they are doing, right? They are doing the earlier smart thing that I explained, like few smartness, they add some code to microcontroller, make something run or whatever. They will add this easily because it's a serial port, right? So there are 2 pins, transmit, receive. You can connect it to, and then they also made available a default firmware which talks AT. So people who have used, I don't know anybody from this group, but in olden days we use AT commands to connect to a modem. So when the internet came into existence in the first time, or when the internet come to India, I think in the 90s, we used to have dial-up modems, right? So how dial-up do when we used to have Windows, and in Windows there is something called a dial-up networking, and when you click on it and then you say show advanced, you will see what is going on, right? So it will say ATT, ATDT, ATDT means AT dial tone, ATDP plus your number, AT dial pulse. So that kind of AT commands, right? So So with that AT command, you can connect to the Wi-Fi. So you write some code, right? So you connect to Wi-Fi and then get some thing can be run within some code, because already the firmware is the intelligent firmware is already there in that controller pre-flashed. So suddenly it became so popular, and then what they did was they published the SDK, software development kit, for generating that firmware, that AT command, whatever the code that is there inside that controller, how they developed, they released the code and they released the SDK. It was 99% in Chinese except for the code at that time. And then the whole community came, and then they used that SDK and they translated, people who know Chinese and English, they translated to English. And then somehow within 1 or 2 years, by 2016 or 2017, it became a big thing. So the company became so big, and people started to put this ESP8266, that was the first one, to all whatever they can make it Wi-Fi enabled. And then they developed a much advanced chip called ESP32, which is a dual core, an advanced LX6 core, and which has got the Bluetooth. So suddenly it became a Wi-Fi and Bluetooth special microcontroller, Wi-Fi and Bluetooth SoC in one single chip, and very cheap. So I think that is one of the key factors behind Internet of Things. Sorry, Internet of Things revolution. And then there is one more thing happening behind the scenes in China. They developed their own architecture. Okay. They developed their own architecture, named it as C-Sky or CK16, depending on the version. And it's based on an old Motorola M-Core, which is now rarely used. They made it more capable. They made it. They developed a few chipsets, and they added 64 MB RAM to it, so people can run a very low configured Linux, or even they can run the normal RTOS. And what has happened is Alibaba, who is one of the biggest cloud provider, bought that company, and released the code, released the Linux architecture support code, got it reviewed, and got it integrated into Linux as a new architecture last week. So it rarely happens after all these architectures we have, right? Very capable architectures. And I think that's the last new architecture that gets developed and that gets added to Linux. So I don't know how much adoption it can come outside of China for this architecture, but there is potential. So those are all those are all the capable architectures for IoT. So having said that, I will also go through the old 8-bit architecture which started all this, right? So there is Atmel AVR architecture. So Atmel AVR architecture is an 8-bit RISC architecture, and it is used in all the Arduino. Arduino is one of the open source, easy to use embedded development toolkit. I'll explain that in detail for those who already don't know what is Arduino. And then there is the classic 8051. Why 8051 is still relevant is, even though 8051 as a microcontroller don't add a lot of value, a lot of development has already happened, right? So earlier, to develop in 8051, there were no free tools. Okay, so either you have to get a commercial compiler from Keel or IAR, companies like that, or you need to pirate it, right? So it's not ideal. You cannot release a product based on pirated code and all. So, but what has happened is, slowly when the Linux gets popular, open source gets popular, people really wanted a compiler for 8051. So they developed and the normal regular open source compiler is GCC, right? So now there is CLang also. The GCC compiler was heavy and not really suitable to customize for a 8-bit very low power microcontroller. So the people started thinking about it, and they developed a compiler called SDCC, and it's called a small device C compiler. And slowly it matured, and now there are many architectures supported in SDCC, and it's a very mature compiler now for 8-bit microcontrollers. Not even 8051, many other microcontrollers. And then what has happened is, right, there is the level of smartness needed has gone so high, right? So we have smartphones. Smartphones runs on SoCs, which is big and powerful that I told. But there are so many other things that's in a smartphone, right? So when the SoC, when we turn the power button off, the whole thing sleeps, right? So we need something to detect when a user has pressed the button, or to depending on how much, depending on some packet, if there is any packet which needs attention in the Wi-Fi or GPS space, all these need some micro intelligence everywhere. If the battery is charged, so people started developing a lot of application specific circuit and started putting 8051 core in it. So now we cannot count the number of 8051 cores in your laptop or your smartphone or whatever other device you have, right? There are at least 10 or 20 8051 core in a smartphone and in your laptop. The battery has battery has a 8051 controller, battery charger got a 8051 controller to add some logic. So that so that's why I thought that I should mention the importance of 8051 in this slide. So let's move to the next slide. So let me explain. Let me give you a brief about what you need from a hardware perspective to get into any of these, right? So if your interest is in embedded Linux development, right? So in embedded Linux is a lot similar to you installing a Linux in your laptop or desktop, right? So you download the ISO, you burn it to USB. In earlier days, you burned it in CD, you put it in startup disk, it boots up, right? So the embedded Linux, when it is installed, right? When it is installed, it almost works the similar way, right? There is a Linux kernel, it boots up. Then it tries to mount the temporary root FS or the read-only root FS or the init FS, whatever. Then it tries to mount. Then it gets the driver to load the file system. Then the file system get mounted, and then it changes the root file system to the mounted file system, and then it starts the startup applications, and then finally it brings up the GUI. So that boot process is almost similar, right? So almost similar means, yeah, it's almost similar. Even the Android phone behaves the same way, right? So but the difference is, majority of the difference is how you package it, right? How you package it, how you install it, and then how you load it. That is the difference between embedded Linux and a normal PC or laptop Linux, right? So in PC Linux, right? So right now, earlier there was BIOS, so you need a different bootloader. So we have Lilo Linux loader, then we have grub. Then right now what has happened is the BIOS is being replaced with a much capable BIOS called UEFI, Universal Extensible Firmware Interface, whatever. That is capable of loading the kernel itself, Linux kernel itself, or Windows NT kernel itself. So you don't need in PC world, right? In PC world, you don't really need a bootloader. But that's not true in the embedded world or in the IoT world. You need something to initialize the basic minimum hardware like memory and all these things, and copy the kernel at least to the memory and then change the program counter and let's say start. Here you go. So for that, there is special bootloaders in the embedded world. So if so, the one of the most popular bootloader is U-boot. It's open source bootloader. So most of the embedded Linux systems, most works on U-boot. So U-boot will load the kernel and U-boot will load the init premises. And then after that, the Linux kernel will initialize the remaining stuff, load the file system driver, and then the file system gets mounted and then start. And second thing is the file system itself, right? In Linux, in a PC world, the hardware, right? The hard disk is always writable. You can even write to the file system files, operating system files, everything. But if you do the same thing, if you do accidentally delete in a firmware-based system like embedded system or embedded router, you accidentally delete, there is no way you can recover. So in embedded system, always the file system, at least one part of the file system is read-only. And then if there is a use case where you want to store some data, right? So you want to add more functionality or you want to save some settings. So either you have a dedicated partition for writing, or you will mount something called you will dedicate some space for another file system and then mount that file system as an overlay file system. And then if something fails after you installing something and something happens, you press the reset button, and what it does is, if the reset button is pressed during boot up, the code will delete that overlay FS, and the system will again start booting whatever is there in the when you bought the product. That's how the reset works in modem and everything, right? So that's the difference between embedded Linux and then the capability and the power is less, and you don't need all the packages. You don't need the packages for video based stuff. You don't need the packages for GUI based applications. That is customizing what packages are bundled, but essentially it is the same. And the one major difference is you may not need SWAP. You may not enable SWAP in a embedded based thing. And then there is embedded RTOS development, right? So there are many embedded RTOS. So like in Linux, you'll have multiple programs. Okay, so and those programs can have multiple threads, and also it's a really like a multi-process scenario in a router or in an Android phone or in your set-top box. All there are multiple applications running, right? So let's say for example, in your router, if it is a ADSL router, so there is a dialer application, right? When you configure your ADSL router and password, when the dialer application makes sure that when it comes up, when there is a dial tone, in it checks for the dial tone, and when it keeps on checking for a dial tone, if there is a dial tone, then it keep on trying to dial the number for the ADSL and try to send the password and username and then try to get a connection, right? So that process is separate. Then there is a DNS, right? So whenever you search google.com, so your browser will send, oh, google.com. Is there do I know what is the IP address of google.com? No. Then it will send to what is the DNS server. So usually your router will be the first DNS, right? So there is a DNS process running, which job is to accept DNS connection, and if you don't know the DNS connection, it will send to your ISP if it is BSNL or Airtel, and then if they don't know, if they already know by cache, it will send it, or they will go to another higher thread tree of DNS, and finally it will get. So that is another process. Then there is a process for the web browser where when you configure your router, you will type 192.168.0.1 or whatever. So that is a web application running in your browser, right? So there are multi-process in play in any embedded Linux application. So if it is Android, there are so many applications which one manages your LTE or 3G connection, one manages your Surface Touch, Surface Flinger, one manages your many to manage your each application. There's so many. So it's a multi-process. That's what in embedded RTOS it gets compressed a lot. There is only one real process running, and that is the operating system. And then you will define multiple tasks, right? So and you cannot install or change anything. So it's very, very, very minute level of an operating system called RTOS. There are many examples of free and open source RTOS, and the most popular right now getting is free RTOS. That I'll come to that. And to get into that development, right? That is the RTOS that comes into play when majorly comes into play when you turn to IoT node development. So if it is a IoT light bulb, IoT switch, all these things, most probably you will have something which runs a free RTOS or some similar RTOS. So to develop an embedded Linux development, you can easily start embedded development by getting one of these boards. Okay, so getting the hardware is not important. We can do with simulator also. That also I will explain a little bit later. So either you can get a Raspberry Pi, or you can get an Orange Pi, which is cheaper, or you can get the C-Sky development. This, if you get a C-Sky development, there is a lot more opportunity to learn because it's just starting. So all the other platforms are much mature, so you won't really play unless and until you are really motivated in actual embedded OS development. You'll do a lot more application development, but not in the board bring up and all those things. So, but if you want to do embedded RTOS development, then you can either get a ESP32 board. It will cost around 300 rupees or 400 rupees. I think that's what Amazon.in told me. Or you can get a Winner Micro one. This is an ARM based one. This is a LX based one. This is dual core and it has got BLE also. So I think it's better to get this one. So you can play with BLE. You can play with this one if you want to really learn. And then there is classic Arduino development board, right? So that's for the non-internet connected development. So you'll get a normal Arduino board. If you search, you will get a normal 80 mega 38 or 8032U4. The 32U4 is a really interesting device because you can do a lot more stuff with it from a USB perspective. So this one has got a USB hardware built in, so you can write code to make it behave like whatever you want. You can hack the systems also. So that's what about the embedded development boards. So now let's define embedded interface. What is an embedded interface? So if you take a computer or a laptop, you have many different ports, right? So you have USB port for connecting your mouse keyboard. You have HDMI port for connecting your display. You have a Thunderbolt port for connecting some cameras and all. There are many ports, right, which are much faster and much high power. Similarly, for embedded interface, right, you need to connect multiple sensors and some small displays to the embedded device. It's also a processing computer, right? So for that, there are many interfaces. So these are the most popularly used interfaces. One is the classic UART, the serial port. Serial port is very important because that is one of the most easier port to bring up. So both, if you're in embedded Linux, both the bootloader as well as the kernel prints the initial boot up stages messages into the UART. So if you connect it, right now there is no real serial port in the computer. So what we normally do is you get a USB to serial interface and connect it to your embedded Linux board, and then open Hyperterminal or Linux Minicom, or there are many different applications you can run to see all these messages and type terminal applications. So that's a very important port even now. It is one of the oldest port. So there are many different voltage levels in this we have to consider. So earlier there was 12 volt level supply for the old serial port. Then people started avoiding the 12 volt transceiver and started directly connecting to the actual controller. So earlier the controllers were 5 volt. So your USB to TTL has to be capable of accepting 5 volt. Now the Raspberry Pi, Orange Pi, all those devices, they don't have any transceiver and they work on much lower level. So they all need 3.3 volt. So USB to 3.3 volt serial port driver, it costs only 100 rupees or 150 rupees to get it. So, but that is a very important device. Then there is I2C. I2C is inter-integrated circuit bus. It's a one master multiple slave bus. So each slave, right? Each slave can be a sensor or a display. Each has got its own address. So the master will address the slave and then send the message, and the slave will respond. So always the communication is initiated by master. It's a very simple bus to interface if you are working in embedded. It just needs only serial data and serial clock, and then connect. So it's very easy. If you have a couple of wires, you can connect easily, and then it's very easy to test. Even if you can in Raspberry Pi, you can directly connect it to one of the pins, a sensor, and then you can use I2C detect. There is already a tool in if you install Raspberry Pi default operating system like Raspbian, it already comes with it. So it's very easy to work with. The number of lines is easy. So anybody with two wires, and then you need two more wires for everything, right? So you need to supply voltage and VCC, and you need to supply ground. So that is common, right? So your hardware is your Raspberry Pi, you will charge with your USB port or whatever. Then your slave device, that also needs some power, right? So for that you need to add VCC and ground, and then do SDSCL. You can interface, and you can interface up to 127 such devices in one single bus, right? There is no complication. It's very easy, but it's not very fast. Okay, it's moderately fast for monochrome display. That's it, but not very fast. Then there is the next level SPI, serial peripheral interconnect bus. That is one bus which is much faster. If you use SD card in your mobile, right? SD card in your mobile is using SPI to interface to the microcontroller, that is your phone's SoC or processor. So that's a three-way protocol. It has clock, and it has master in, slave out, and master out, slave in. Two lines for data, and then there is no address for a SPI device. So how they will do is they will use separate switching lines called slave select or chip select. So SS, slave select. So this is the master, which is your processor, and you can connect the same bus. That is these three lines: MOSI, MISO, serial clock to all the devices. If you have 10 SD cards in your device, you can connect these three lines same parallelly to all the devices together, and then you use different lines to switch it on. So at a time it will only one device to master communication is possible, but after that you can switch off that line and switch in this line and make this active. That's how the SPI communication works. Then there is something called CAN, controller area network. So that is one of the most popular bus used for communication between various different computers inside a automotive. So if you have a car, and if it is manufactured after 1996, there is a CAN bus, right? So your display, which displays your how many kilometers the car has run, what is the speed, all those are transmitted from the ECU, the engine control unit, to display in the OBD, in the cluster. The cluster, the speedometer, that part of thing is called a cluster if you come to automotive, and then that cluster will display. So if you have an expensive car like BMW, Audi or something, and then there is a black market device, what it does is, if the car has run 300,000 or 3 lakh kilometers, you connect an intercept device between whatever the ECU plug and then to the cluster, and you write a code. If the message is Odo, and if value is greater than 1 lakh, reduce 1 lakh. So your 1.5 lakh driven car will show only 50,000 kilometer, and you can sell it for high price. So there is a black market device which you can build or you can buy and program. So if you have 300,000, okay, make it 300,000. Anything above 100,000, make it less than 50,000. So similar, there are so many applications, so many things which talks to that through that bus. It's a single bus. It's daisy chained, and it can be multi-master. So that you can read through how it became, how one. So there is something called bus arbitration. So because it's a common bus, who can talk, that happens. So anyway, it is only two line, can high and can low. It's almost similar to RS485 if you have learned RS485. Anyway, so that's a popular bus in CAN, and it supports a longer distance compared to SPA and I2C. I2C and SPA most probably it's in the same circuit board you can communicate. If you want to run between car from the end to the front, the CAN is much more suitable. Then there is GPIO. GPIO is just high-low. You can connect directly to LED bulb. You can turn it on, turn off, right? But what level, it can be different. But mostly it is 3.3 volt if you are talking about Raspberry Pi or ESP32 and all. So it can be, you can connect that to LED. You can connect that to relay to turn on off. You can connect to actuator to open the door. It's like on off, right? It's a signal which is on off. And then if you write the on off action and see if you can turn, or you can take one GPIO pin, turn on off on off on off. It became a clock, right? It became a square wave clock. And then you take multiple things and you can do it in software. You can emulate others. So let's say, for example, your actual microcontroller don't have I2C, yeah? And you need to communicate to I2C, and it has some GPIO. Using software, you can emulate the I2C protocol and send it, but it's much harder. It became very tedious to debug and all those things. But still, that's one use case for GPIO. Then there is PWM. PWM is pulse width modulation. What happens is, right? So I said that GPIO can turn on, turn off, right? So turn on, turn off. If you use that for charging a capacitor, it takes some time to, if it is a 3 volt turn on, right, 3 volt GPIO, you connect a capacitor, it takes some time to reach that 3 volt. So if you turn on the 3 volt for very little time, it won't reach 3 volt. Before the capacitor can charge up to 3 volt, it gets off. So that way you can control, or you can simulate an analog waveform through pulse width. So that's called pulse width modulation. And if you want to do it using software, you have to really write brilliant code to define how much time you have to utilize based on what is the analog signal that you want to emulate. But there are many hardware PWM where you say what is the width and what is the cycle. You can emulate almost equivalent analog waveform through pulse width hardware. So that's what pulse width modulation is. So these are the most important interfaces from a embedded SoC or embedded microcontroller. So let's go to the next topic, embedded peripherals. So I'll quickly go through this. There is embedded sensor. There are sensors which can sense temperature, humidity, pressure, light, contact. If you want to develop an application based on agriculture, there is soil moisture sensor. And there is input devices like push button switches, keypads, rotary encoders. Rotary encoders are something like the volume control, but we can use it to control the interface. And then there are displays, character LCD display like the old character LCD that you used to see in some old Singtel cell phone. Then there is mono OLED display like this one, where you can display some graphics. Then there is color LCD display where you can actually display some full color pictures and all those things. Then there is 7-segment display for actually if you really want to display only numbers, like that is in the weighing scales in the grocery shop. Then there is a dot matrix display also for using LED, which is monochrome. Then there is a other color matrix also based on what you call pixel dot and all those technologies. But anyway, these are. Then there is actuators. Actuators are something which physically moves, right? So there is motor-based actuators like this, and there is also solenoid-based actuators like your calling bell, the normal calling bell, not the music one, ting tong. So when there is a charge, it will push the rod to something similar. That's a solenoid based. Then there is motor based, which will turn either rotating motion into angular motion or rotating motion into linear motion. So this is a linear motion used for curtains and also. And then there is relay. Relay is for turning on heavy load equipment, right? So if you want to switch on, switch off heater, all these things, they need a relay, high power handling. So relay, you can control a relay from an input from a GPIO. So there are multiple types of relays. One is a mechanical with a coil. Then there is something called solid state relay, which don't have any moving parts, but it gives the isolation of an actual relay, but it don't have. It is based on FET and Opto isolator, but you can read it up later. And there is so a relay. If you want, relay always goes in one position, either off or on, right? And if you want to turn it on, you need to apply power. As the moment you take the power off, it will go to the last position, either on or off. Most probably off, right? And same thing with this thing. You want the signal always. And there are some applications where you want to maintain the state. That's where the bistable latching relay comes into picture. A bistable latching relay has two coils. So if you apply one signal, if you apply power to one coil, it will move to one side. And if you apply to another coil, it will move to the other side. So one side will be off and the other side will be on, similar. So that will maintain the state even if there is no power at all. So that is one. In some special cases, you can use that bistable relay. Then there is indicators, LED indicators or flashing indicators. That's just GPA connected to some amplifying device and connected to or directly to some LED. It's an indicator. Then the camera modules. That's mostly used with SoC, especially in internet connected cameras, and also there is a bus called MIPI CSI. Camera system interface. So that one you can use this with Raspberry Pi and you can try some AI face recognition and all. Then there is real-time clock. That's when you need to have really your application needs actual day, date, time, and if it needs alarms and interrupts, if it needs to go to very low power state and only wake up when there is in one particular day at what particular time. So that kind of application is real-time clocks. So real-time clocks runs on this button cell and it will keep the time, it will keep running for 10 years, 20 years with this battery. So you always get the right time. So irrespective of whether the power goes on or off, you can always rely on this time to decide what to do. So those are the applications that needs RTC. Then there is ADC and DAC. So if you want to measure something, measure some analog value, like how much moisture is there in the soil, or how much humidity is there in the air. Should I turn on the moisturizer now or not? What is the temperature? Should I turn the AC now or not? All this to measure the analog value and see and process it, you need ADC. And similarly, if you want to convert a digital value, you calculate some value and now you turn it into an analog value, like the brightness of a bulb, you need DAC. So as I mentioned before, you can use PWM to convert a digital value to AAC, but there are some special high precision requirements where you will get like audio, like so you have MP3 and you need a better DAC to have good quality audio. Audio is an analog signal, right? So that is where DACs comes into picture. So now let's go to ISM bands. So what is ISM band? It's a spectrum. It's a band from the wireless spectrum. So ISM band is a set of frequencies reserved for industrial, scientific, and research purpose, and also for anybody who wants to try something, they can use that. That's why we don't apply for a license when we want to buy a Wi-Fi. That's why we won't have to apply for a license. If you want to, radio normally is a license controlled, right? Every country has got licensing authority and all. So ISM band is a set of frequency which is reserved for free use. So Wi-Fi uses ISM band, and 2.4 gigahertz is one of the most used Wi-Fi band. So in this picture shows you how the Wi-Fi is allocated, right? So 2.4 gigahertz, 5.8 gigahertz, 900 megahertz, these are all free to use Wi-Fi spectrum. And so you can see how channel 1, channel 6, and channel 11 are allocated, and in between there are many other channels, and how Bluetooth also uses the same channel, but how it does is Bluetooth will shift the frequency 1600 times per second. So it will always advertise in these three frequencies. That is I think it is channel 37, 38, and 39, or 2402 to 4, whatever it is. And then it will, when the actual during actual communication, it keeps on shifting. And then newer Bluetooth, what will happen is, before trying to connect, it will check what are the frequencies that is already in use and avoid those frequencies before choosing the frequency. So if it is Wi-Fi channel 1 is already your Wi-Fi router in the home, the Bluetooth connection won't use that. So that's what the ISM band is. And all the IoT stuff relies one or either way in this using these ISM bands. Then Arduino. So Arduino is a free open source software. You can install. You don't need any hardware for it. You can just install in your Windows or Linux or Mac, download, and it's free. What it does is, so I told about the compilers, right? So compilers, if you compile it for your PC, it's called compilation. If you compile it for other microcontroller or micro SoC, it is called cross compilation. So Arduino collects all the tools needed for compilation, linking, and uploading or flashing to a development board in one nice to use software. And you can just and sorry and make it very easy to program, even easier than programming a normal JavaScript to program a embedded device. So it's just a classic Arduino relies on just two functions: setup, which is the initialization. So in this particular example, you set up one pin of the controller as output, and then so you define the pin number is 13. First, you define pin number 13 as LED pin so that you don't have to remember 13, 13, 13. So then pin mode 13 to output, then right to high, the LED goes up. It will wait for 100 milliseconds and then 1000 milliseconds, 1 second, and then it will write low. Low means 0 to LED pin. It will turn off. So it will, this particular program, if you just copy paste into this, then compile it, it will run and produce the binary. And then if you click on that right arrow, it will flash. If you have already connected this to your USB port, it will flash and it will automatically start blinking the LED. And normally all Arduino board has got one inbuilt LED, so it's very easy to get into. So that particular program is written in Java, and now it is not looking that good. The Arduino is trying to develop a new modern interface, but people have already found an alternative, so they use Microsoft Visual Studio, which is an open source editor.
Excuse me, sir.
And, yep.
Yeah, just a time reminder. It's now 1:25 here.
Okay.
Okay.
So how much time I got?
10 to 15 minutes. That's
yeah,
it.
sure. Okay, so this so Visual Studio Plus Code is another good good alternative to that. You can use the same Arduino code using Visual Studio Plus Platform IO. And then so as I mentioned before, FreeRTOS. So FreeRTOS is a fully open source operating system. So the one good thing about FreeRTOS is that if there is already a library for Arduino, you can just install Arduino library FreeRTOS, and you can just start using the Arduino itself to develop FreeRTOS application. So the only difference is, as I mentioned before, there is setup and there is loop. So in loop, where you will write continuous application, in FreeRTOS case, you will leave the loop behind. You will just create X task, create functions to register the task. Those tasks will keep running anyway, so you don't need to write anything in the loop. That's the only thing that you need to remember. So yeah, the task can be either suspended, ready, blocked, or running. So you can, in the task when you run, you can do it you can set the state of the task so that you don't block the CPU. And then, so what has happened is recently Amazon adopted FreeRTOS for Amazon AWS IoT. So what the Amazon did is Amazon added a layer of functionality to FreeRTOS so that it became very easy for you to connect to AWS IoT backend. And then a lot of libraries were added for Bluetooth low energy and then AWS IoT green grass and all. So you can check that, and that is why I said FreeRTOS is very important because it's getting a lot of adoption. And then there are other alternatives to FreeRTOS which are also equally good. There is Mongoose OS. If you are not really focused on Amazon OS and you want to integrate to either to both Amazon GCP Azure, Mongoose OS is one RTOS that you can consider. Mongoose OS also gives you a web-based configuration tool, so it makes very easy to run and develop. Then there is Zephyr OS. Zephyr OS is Linux Foundation endorsed. If you have tried Linux kernel compilation and all, it's much easier to understand Zephyr OS. So the concept is all same. So you will have a scheduler and you will define a number of tasks, right? And then there is embedded, which is ARM, dedicated to ARM. If your microcontroller platform is ARM, then you can consider Mbed. Mbed has a web UI and Mbed has a cloud, so you can register to arm.embedded.com, embed.com, and register an account, and you can start compiling and developing from the browser itself. You don't need any installation, you don't need anything. Just a browser page, you can create an account and start. So those are the alternatives. Then there is embedded Linux, right? So embedded Linux is optimized for read-only root file-based applications, like I mentioned before. So almost till now, because FreeRTOS is only coming into picture now, till now anything internet-connected device used to run embedded Linux. So that is one huge chunk of the market. And normally, if you are into IoT without Linux or without embedded Linux, there is very less chance that you will work. So that's one area that you can focus, and it's very easy to learn because the OpenWRT framework is there. So you can go to www.openwrt and then click on build, how to build. It's very easy. You can just copy paste the commands there and run the commands. It will allow you to initially compile one firmware based on whatever device you chose, and also you can run for virtual environment like QEMU, so where you can build and run in the PC itself using emulation and try your code. It's very easy to add device support because already it's all well defined. You just follow the process, you can get it running. Then, so like OpenWRT is very popular because it started a lot earlier. Similar frameworks are there, like OpenWRT for building the embedded firmware based on Linux. So Yocto, Buildroot, Monda Vista, and WindRiver. Monda Vista and WindRiver are commercial. So if you join a company and they are building some firmware, most chances they may be using some commercial tools like Monda Vista, WindRiver. But the idea is all same, right? They build a firmware, they build the kernel for your hardware, they bundle some application, they build a bootloader and make it everything in one file to be flashed into the flash or whatever. So it all does the same thing. So only the way it does is little bit different, that's all. Another thing, very important topic in IoT, especially when it is home automation, is ZigBee. So ZigBee is a wireless protocol. ZigBee is a mesh networking. There are three things in ZigBee. One is coordinator, one is router, and one is end device. End device is your bulb or switch or sensor or whatever. Router is your smart socket plug or something which always connected to AC. The router extends only to increase the range. The core logic is in the coordinator. Coordinator connects to your internet connected or network connected device like a Raspberry Pi or a router, and then from there the internet protocol will comes into picture, and it will send to the application in the cloud or web, and then it will send a message to all the patterns that I discussed before will comes into play. So Zigbee uses mostly Zigbee uses the same ISM band as 2.4. Then there is Bluetooth and BLE, which is already very popular. It's mainly used for personal area network like your headphones and mouse and all. But with the addition of BLE, it's also getting some traction in home automation. There are some sensors which uses BLE, and human presence detection using BLE is also comes into picture. So when the mobile phone comes into range of one particular BLE node, they can sense and do action like turn on the TV. Or there are other applications also like display beacon, which is commercial. Like there is a beacon concept in BLE. So when the shops, in shopping malls, they will put beacon in the shop and register that beacon with a central application. The mobile phone gets they keep on sending a message. Mobile phone get that message and that sends to the cloud. And the from cloud it will get a notification like some special offer for this shop. So that's a commercial application for BLE. So anyway, so that's one technology. And then for automation, so we talked about sensors, we talked about embedded and all these things. That's all for the node, right? Then for how to automate, how to write the rules, right? So there is a free software called Node-RED. That's a software developed originally by IBM. So it's a visual programming tool. So what does that mean is you don't need to code. Okay, so you create objects and then you wire it, right? So this particular example shows somebody wired a ceiling fan. Somebody wired a ceiling fan command from Amazon Alexa. So when say ceiling fan, so it will format a dimming value. So ceiling fan low means it will format that value and send a HTTP request to the Wi-Fi enabled ceiling fan controller. So similar thing you can do just by pick and choose, and then wiring, just connecting the wires. You can architect a whole flow, whole logic. That's Node-RED. It's very difficult to explain what is possible, but you can install Node-RED and type, or if you have Raspberry Pi and you install Raspbian, it's already there. Just try it and you will come to know. Then there is another tool called Home Assistant and Domotics, which is primarily focused on home automation. The earlier tool Node-RED can be used for anything based on rules. This is a little bit more focused on home automation. Then there is another very important technology called LoRa. LoRa is a long-range radio. It works on either 915 or 868. The difference between Zigbee, BLE, and LoRa is that LoRa covers kilometers, more than 10 kilometers you can send. So the same pattern, but on an agricultural or industrial setting, you can use LoRa. So LoRa needs a gateway which is bit expensive than Zigbee. Zigbee you can use for 500 rupee dongle and a Raspberry Pi or your laptop itself to start with. But LoRa needs a gateway which is around, I think, 8,000 or 10,000 rupees or $150. You can use a LoRa Shield for Raspberry Pi also, but anyway, that is still cost almost same thing. But once you have the gateway, right? So the application range is much higher because there the applicants are more serious, right? So automating and helping an agricultural field is a much more important stuff than turning on your light bulb or switch, right? So that LoRa gives that capability, and I think in India the LoRa uses 868 megahertz. and then you don't need so the whole LoRa stack is open source. If you go to chipstack.io, you can see the LoRa, all the software that's needed to create your own LoRa network. But you don't need that. There is already a cloud-based provider which provides the LoRa network backend, which will make wiring up the things a lot easier. So all you need is a gateway configure, create an account in thingsnetwork.com, and configure your router in that, and then you are part of the whole world network. You can access that from your application in the AWS cloud, and it became very easy. So all these protocols work on a backbone called MQTT. So message queuing telemetry transport is the HTTP protocol of IoT. So it is designed to be around the same publish subscribe concept of a message queue, and it also uses the same high quality security like TLS. The HTTP works on port 80 and 443, but MQTT works on 1883 for non-encrypted and 8883 for TLS encrypted. And then MQTT over WebSocket uses the same HTTP protocol. So that's one protocol which is very important in IoT space. And then there is an open source broker called Mosquito, which you can easily install in any Linux-based operating system and Windows and Mac respective. So that take care of the handling of the MQTT transport, and then your application in the cloud can be one subscriber or publisher to that, and you can make the whole application go way beyond your local network. Then there is REST API. REST API is the database language of the cloud. Okay, so you have select, create, update for SQL. So same thing over internet. You will use the in the internet when you create www.google.com. Once you get the IP address, your browser will say get /index.html. If you don't specify any path, that's how it works, right? So then there are other not mostly used verbs for HTTP. So REST, what does REST does is REST uses those put, delete, post anyway you use in HTTP. So REST combines this most used get and put, and then not that much used put and delete to form a full CRUD operation, create, read, update, delete operation over browser, over HTTP protocol. So your Android application and all or your Android application and your IoT based web application all uses REST based protocol to communicate. So so you can have a backend which translates the MQTT to REST and enable REST endpoints integration also. So REST is something which you should be really so HTTP uses HTML encoding. REST mostly uses, you can use HTML encoding, there's nothing stops it, but mostly we use JSON as a format for transmitting and receiving application information. So what are the common problems to solve, right? So in IoT space, when you create a new application, onboarding devices to network, that is one major area where always there will be some development needs. What does onboarding means? When there is a device you manufacture from a factory, you packed it, you shipped it, and it comes to your customer, right? So when the customer tries to connect that to thing, how do you safely and securely authenticate? You create an account, then you connect that account to your device, and then you somehow transmit the device to have a secure credentials without leaking, and then establish the connection. So onboarding a new device to a network is a very challenging area, and always there will be development. Then there is a security privacy issue. So because everything is going to go through internet, so it's always need to know, right? So if you have to, your bulb shouldn't be able to, your switch shouldn't turn the light out of your neighbor's house, And then when you are turning on bulb, when you are turning off light, that and all that information nobody needs to know, right? So that how you and make sure that the encryption takes care of that. Then there is productization, right? There is a lot of open source tools that we discussed, right? Then how to customize all those, package it, everything, and make sure that it works nicely, it works every time. Even if something goes down all around, say like Amazon cloud goes down, all your application goes down. How to make sure that it comes up, and as soon as Amazon comes up, your application should be totally as scripted and as part of as a code, so that when you run it, everything comes back as it is before, take the backup and everything rest. So that's productization. Then there is integration, right? So there are so many components together. There is Android application, there is bulb, there is switch, there is another web based portal. All these things need to integrate and make sure that everything is in sync. So there, that a lot of glue code needs to be written. So that's where one area where you can start. You can try all these tools that I discussed: MQTT, Node.js, AS.io. You can try connecting each other. All these things you can understand that one. Then there is branding, right? So branding means just customization. If you are working for a company, all these things, all the customization needs, and if you have value adds, right? Or the company has already an existing line of products, how to integrate that, how to all those things. That's normal stuff, which is mainly purely marketing, but still. So okay, so let's talk about open source projects, right? So open source software collaboration is already very highly mature. So you create an account in GitHub, you create an account in GitLab, start doing it, create, say, let's say, if so, here is the deal, right? If you have an idea, you don't know how to solve, right? You create an account, you create a project, you say that this is what I have to do. I don't know how to do. This is what I have to do. Automatically, the community activity will help you how to achieve it, and people always is interested to contribute the code, and so that's all you need. So try to learn Git. Git is the only version control you need to know now. Earlier there was CVS, RCS, Rational, so many version control tools and so difficult. Right now you just learn Git and that should be enough. This thing, and whatever the GitHub or GitLab, the you just need to know the basics of how to use the Git. What is the process to push, upload code, push, pull, clone, merge, um, then how to create a pull request or merge request. These are the only operations that you need to learn, and you can work in any project, whether you work in web development, or you work in embedded development, whether you work in Linux kernel development. 90% of the version control happens in GitHub, and not in GitHub, Git based tool. So GitHub is a public based tool, but same thing applies. Then open source schematic. If you are interested in electronics and if you like to design, you can use open source tools like KiCad or web-based tool like ECEDA. ECEDA is already integrated to PCB manufacturing. So if you have a design, you can even manufacture it from the web browser itself. It will automatically push to the web Gerber files to the cloud-based provider. You pay through your PayPal or bank account, and they will post automatically to you the complete PCB. It is that easy now. And then if you have the PCB, you have the device idea, you can put it into a real product like a Amazon, like a smartphone or like whatever, using 3D designs. There are so many 3D designs already created freely and open source, open source plans and open source schematics. You can directly go to this website, download it. If you have a 3D printer like 5,000, 10,000 3D printer, you can print it. Your device is in your home. All it takes is some plastic filament. Or I think some of these websites already got an integration to companies which prints these designs and send it to you. So even designing a full-fledged product-like looking gadgets is right now free and open source and accessible to anyone. What about open source integrated chips? That's one huge topic. It is not easy. So you can use KiCad, easier to do PCB. and schematics, and then you can use 3D printing or 3D printing websites to design and print your designs. But open source processors is not easy. There is open source code for processor cores like RISC-V, but to manufacture a design into processor is very difficult because you need a foundry. Foundry is very expensive, and there are very few foundries like TSMC, Intel, global foundries. Very few companies which are very multi-billion-dollar companies, and you need at least 10,000 chip order to get it. That was till last month. Last month, one big thing happened. Okay, so processor coding or development of processor or integrated circuit chip is almost equivalent to low-level programming. Your Verilog VHDL code, that's the code used for developing microchips, is almost similar in complexity to a low-level C programming or embedded programming. But the problem is embedded programming you can flash to embedded device. But a microchip design you can there is now where we can apply somewhere and see. You can use FPGA and still it's not the real thing, right? So, but what Google has done is Google has had a tie-up with TSMC. I think they bought a TSMC foundry and they have something called Skywater. And last month, what they did is they have the process node for Skywater. So your process design is only one part. You need to convert it to PDK language to send it to a foundry. So Google, for that you need PDK, process development kit or process node development kit, something. So Google made the PDK for this Skywater foundry, which is a little bit old, 130 nanometer like Pentium for that era, but still you can design a lot. You can design much better processors with that, processor microcontrollers at least with that. And they made it free. They made it not only the PDK free, they are doing free runs. So if you if you copy paste the RISC-V code, put some other free code and make it one processor, and then send it to Google or Skywater PDK website is there. They will manufacture, I don't know the number of processors that they will do it for free, but they will manufacture your microcontroller for free. Already there is a scheduled run for November and there are multiple runs for 2021. So if you are interested and if you are really want to take the challenge, go to Skywater website, search for Skywater and search for RISC-V open source code, search for some other whatever the I2C code or SPI code or even display some HDMI code. There are so many free cores. Just make all the code together, make sure that there is a port and it is connected, send it to Google and type something that this is what my idea is and send it and you will get your microcontroller shipped to your home. So that is what is happening. So the times have never been better. Now is the time to be a technical, to be in the IT and to be in the IoT world. So then for embedded system development, these are the useful tools, right? These are not mandatory. So these are the tools that we can all together you can get for 1,000 rupees or anything. One good lunch at a hotel, you can get all the things that you need. So a cheap multimeter, all these are available on Amazon.in and it will come if you just click. So this is the cable that I told about, USB to TTL, which you can use to debug a serial port. Then for breadboard, you can do mail to mail, pin to pin connection if you use breadboard, if that's the thing. Soldering iron rarely used. If you have a soldering iron, then you need lead and solder paste anyway. Then this is another most important tool if you are working on interfaces, right? So if you're connecting I2C, you send a command to get the humidity. You always get 100 degree and it's a room temperature. What is happening? So if you want to analyze this particular tool, is called a logic analyzer. So what you do is, so I said I2C go to SDA, STL, right? So you connect this is connect to 1 and 2 USB port. You download a software called SIGROC Pulse U, and then you start capturing, and it will show the signals, digital signals, and also it can add a protocol decoder. So if it is I2C, you can add a protocol decoder for I2C, and it will show what word you are sending and what word you are receiving. So this kind of tool before used to cost lakhs and lakhs of rupees, and it was never available. Now what has happened is people used an open source project, build a clone of Cellogic. Cellogic is a company which initially come up with this idea. People recreated that Cellogic, and you can see, you can buy this for 300 or $5 or $6 in AliExpress. I didn't check in Amazon.in. Maybe it is there also. You can decode, and the debugging is very easy. So you don't have to. So okay, so initially when I was coming out of, or I was in the college studying computer science and computer communication, the embedded was never an option. Meaning 1% of 100 students, 1% of the classes will get into embedded because it's a lot of connection wires, and all computer science students now was never into that. Electrical and electronics. In India, it's only electronics, and in US, if you go, it's electrical engineering and electronics sometimes. Uh, these people only used to work in embedded. What has happened is the electronics and electrical guys don't have that much exposure to actual data structures and algorithms and all. When they started, it is perfectly fine because the application domain is very simple. It's just always one loop, and all the logic they will put in one loop, and they will say, okay, this is the application, right? Right now, it is multi-threaded, lot of data you have to handle. So electronics and pure electrical and electronics can never cater to the complexity that is required unless and until they learn computer science, or computer science learn little bit basics of electronics, which is not that hard. So that's why you should never judge the book by the picture. So embedded and IoT is as much a computer science subject as an electronic subject. So I am a purely computer science background, right? Uh, so you can take my example, whoever is interested, and then get into this topic. And so right now, this final word, the technology is never a problem, is never hard. Okay, 90% of any solution is already there as code, as ideas, as 3D, as PCB schematics. All you need is integrating. But integrating for what is the problem, right? So if you are starting your own company, if you are starting your own hobby, you choose a problem that is very important, and you think that can change the world. You take that. You don't need to be an expert in all of this stuff, right? You identify the problem, and you at least visualize how this problem have to be solved, or what is the ideal state, and then just created that statement in GitHub or any community portal, and people will keep on coming with ideas, people will keep on contribute to the code, and then you will, in that cycle, you will improve all your areas that I discussed. You will automatically improve. You don't need to actively pursue and learn each and every technology that I mentioned. I didn't learn each and every technology on that one. I learned all those things on the way, right? You just need to be aware of, okay, there is a Zigbee for this. You don't need to learn how Zigbee works, how to connect Zigbee. You will come to that when you use that for solving your problem. So problem is important. Second thing is solve it right and solve it for everyone. Try to be open source, try to get into a project which is open source, try to actively contribute to open source, and always be a hobby in the open source world. Even if you are working for a company which is don't care about open source, you always keep running in that in the background, and always success always trails. So right now, goodwill is more important. Goodwill, success always brings to people with goodwill. Later. That's all my final statement is. Thank you a lot. All the best.
Thank you. Thank you, Jiva sir, for the wonderful and informative session. Now it's a turn for audience. If you have any queries, you can ask now. Towards the audience, if there is any clarification or doubts regarding the topic, you can ask now. Okay. So expecting you are all clear with the topic. Time is exceeding for all of us. So thank you, Jeevas sir, once again. And for the official vote of thanks, I invite Mr. Anil, Assistant Professor, Department of Computer Science, Yuvakshetra College. Welcome you, sir.
Good afternoon to all. Respected Director, Reverend Dr. Matthew George, Principal, Dr. Tommy Anthony, Vice Principal, Reverend Dr. Lalu Velikil, today's resource person, Mr. Jeevas Vasudevan, HOD, Ms. Meena Joskomban, academicians, faculties, and students. First and foremost, I thank our resource person, Mr. Jeevas Vasudevan, for the interesting and highly informative session. Thank you, sir.
Thank you.
On behalf of the Department of Computer Science, I extend a very hearty word of thanks to all the members present here. My sincere word of gratitude to our beloved Director, Reverend Dr. Matthew George, for gracing the occasion. Thank you, Father. I also mention our deep sense of gratitude to our Principal, Dr. Tommy Anthony, for providing encouragement behind the webinar organization. Thank you, sir. I wish to express our sincere thanks to our beloved Vice Principal, Reverend Dr. Lalu Velikil, for always being an inspiration and support. Thank you, Father. I thank our HOD, Ms. Meena Joskomban, for the moral support and guidance provided. I extend this opportunity to thank my entire team for the enormous cooperation and contribution for the success of the international webinar Light My Fire. Last but not least, I thank all participants who attended this international webinar session. Thank you all. With these words, I conclude. Thank you.
So that was the official end of the session. We'll see you all tomorrow and day after tomorrow for the coming sessions. Okay, tomorrow's time, can you please note the time? That is 2 to 3 p.m. So hope you all enjoy the session. Thank you once again on behalf of Yuvakshetra College and Department of Computer Science. Thank you, Jeevas sir, for sharing your time, valuable time with us. Thank you, sir. Thank you all the participants.